Hi, I'm Zhang from the University of Oxford. I'll be presenting OneLabeler, a flexible system for building data labeling tools. This work is done in collaboration with Yun, Haidong, Bing, and Dongmei from Microsoft Research Asia, and Siming from Fudan University. Supervised machine learning requires labeled datasets to train models. Different machine learning applications call for labeled datasets of various modalities and tasks. Repositories, such as Paper with Code, have indexed machine learning datasets with tens of data modalities and hundreds of label tasks. Example data modalities include image, text, and video, and example label tasks include classification, segmentation, and named entity recognition. Different scenarios require different labeling tools. The labeling tools may accommodate specific data modalities and label tasks. They may integrate techniques such as clustering data points and proposing tentative labels to provide machine assistance to annotators. Existing labeling tools usually target a specific usage scenario and are hard to customize. Meanwhile, developing these labeling tools is demanding for the developer, as it requires cross-disciplinary expertise. The developer needs to know interface design, machine learning, and have solid software development skills. In this work, we investigate how to make labeling tool development easier. We aim to build an authoring toolkit to ease development. The toolkit should build on a modular composable design with unified APIs, enable reuse, and support visual programming and static checking. To meet the design requirements, we need to identify reusable modules in data labeling tools. We collected 36 flowchart figures on the human-computer interaction workflows of data labeling tools in the literature. The 3 figures in the middle are examples of them. Then we go through a coding process. We group the modules and states in the flowcharts into themes, and filter the themes irrelevant to data labeling. Through the coding process, we identified 8 types of common modules, such as interactive labeling, data object selection, and model training. The modules are blocks in flowcharts. We also identified 5 types of common states, including data objects, labels, samples, model, and features. The states are inputs and outputs in flowcharts. Combining the modules and states, we get API definitions of modules in data labeling tools. Each API can be implemented as human computation, machine computation, or mixed computation approaches. For example, the data object selection module decides data objects labeling priority. It can be implemented as an active learning sampling strategy, which is the machine computation module. The strategy may decide to sample the data points whose labels are most uncertain, as estimated by a probability-based model. It may also be implemented as an interactive projection, which is a human computation module. The user can multi-select in the projection to decide data objects to be labeled. Based on the identified common modules, we developed OneLabeler, a visual programming toolkit to simplify the development of data labeling tools. Using OneLabeler, developers can develop data labeling tools by visually configuring workflows. In the visual programming interface, through different workflow configurations, various data labeling tools can be generated. Here we list some data labeling tools built with OneLabeler. They cover various data modalities, such as image, text, video, audio, point cloud, and web page. They cover various label tasks, such as classification, segmentation, and temporal and textual span tagging. Some of them incorporate machine assistance to accelerate the labeling process, such as providing machine-predicted default labels and using active learning strategies. OneLabeler builds in various functions to support labeling tool development. To provide the developer real-time feedback, OneLabeler provides a preview of the built labeling tool. The developer can conduct single stepping and inspect the states of the labeling tool. OneLabeler statically checks the data labeling tool built by the developer and provides instructions for correcting mistakes in the workflows. The static checking saves user efforts in runtime debugging. By iteratively resolving the issues, the developer is smoothly guided to a feasible solution. OneLabeler also supports customization to enable developers to extend OneLabeler's representation ability. The customization requires coding in JavaScript. To scaffold customization, OneLabeler's command line interface enables the developer to start with template code files instead of starting from scratch. We conducted an evaluation with 8 developers. Each participant received a 30-minute training and was instructed to carry out 4 reproduction tasks. The figures on the right show reference solutions for the 4 tasks. In each reproduction task, a detailed textual specification of a data labeling tool is provided to the participant. Using OneLabeler, the participants developed labeling tools with on average around 50 minutes, compared to weeks without OneLabeler. Meanwhile, participants' failures are caused mainly by unfamiliarity with web development. This implies future opportunities to lower the skill barrier on building customized extensions. In summary, we have identified common modules in data labeling tools in the literature. Building on the common modules, we have built a visual programming toolkit called OneLabeler. It builds in various implementations of common modules in data labeling tools and provides development support features. It enables developers to build customized data labeling tools efficiently with no code or less code. Thank you. For more information about OneLabeler, you are welcome to visit our project website.